So, good morning, everyone. Happy to be here. I'm Oskar Elek from UCSC. I'm a postdoc at the Computational Media Department at Creative Coding Lab. We'll also be sharing this talk with David Abramov, who's a PhD student in the same lab. Part of this work is also Joe Burchett and Angus Forbes, both from UCSC. Joe is an astronomer who recently joined the New Mexico State University as a professor, and Angus is a professor at UCSC, leading the Creative Coding Lab. So this is going to be about Cosmic Web, and it's kind of a multifaceted talk. So let's get into it. So Cosmic Web, most of you might know, is this enormous intergalactic mesh or web, connecting all of us together in one happy family. It's a structure that has been evolving pretty much since the start of time as we know it. So the reason why it looks the way it does today is because of this evolution. So it started as a very homogeneous, diffuse, cloud of matter, and then through gravitational condensation and dark energy repulsion, whatever that is, it kind of got shaped into what we see today. Well, actually, we don't see it because when you point the telescope in the sky, you don't actually see the cosmic web. And so the main purpose of the work in this talk is to actually discover it, so to say, examine it, investigate it from multiple different views. I'll talk about it in a second. We can sort of see the cosmic web indirectly. So for instance, this is the cosmic background radiation as captured by the, multiple missions actually. And in this data, you can actually see kind of the footprints in this heterogeneous distribution of the temperature across the sky, but it is not enough to actually reconstruct the cosmic web or analyze it very well. So the best tool we have to understand the cosmic web is simulations. So these are Eagle and Bolshoi-Planck simulations from recent years, as well as the Illustris. I forgot to write Illustris, but this is the Illustris TNG100 data set, very recent state-of-the-art cosmological simulation. And this is actually rendered in CosmoVis, which is, a tool that David will be telling you about. So the tasks for this work, there's several of them, so I'll briefly fly through them. If you'd like to hear or read more about details of these, we have an entry into a recent data challenge within the Visastro workshop. So we describe all of this there. But basically, we are interested in the cosmic web in all manner of aspects. So first of all, to actually reconstruct it from observed galaxy data, to get the structure of all these filaments, the knots, the voids of the cosmic web. Then we want to learn the density of the cosmic web in different parts of the structure. So in relation to galaxies, for instance, here you see kind of a red, green, blue breakdown of the densities in a particular slice from the simulated data. We're going to visualize the star formation rate in galaxies and halos in the universe, and actually find out what is the relationship between the star formation rates and the position of these galaxies or halos in the cosmic web. We also want to investigate properties and formations of the gas, the interstellar and intergalactic gas surrounding the halos of the galaxies. So here you have a bunch of blue filaments, and then this yellow medium is actually the intergalactic gas contained in the halos. We also want to understand how the orientation of the filaments of the cosmic web relates to the orientation and positions of the galaxies. So this is a reconstructed orientation map that comes from our software, where you have these directions color-coded. So vertical filaments are blue, horizontal are green, and then the ones that will kind of pierce the screen would be red. We want to study the impact of the galaxy feedback. So basically, whatever processes go on in the galaxy, how they transform or impact the medium surrounding the galaxies and also the intergalactic medium contained in the filaments. And finally, we want to explore the formation of the warm-hot or WIM intergalactic medium, which is a very important constituent of the cosmic web. So here that would be kind of the yellow-orange medium interconnecting the big halos. So there's a lot of information. Again, you can read about it in that paper that I mentioned. But to actually do this analysis, we rely on two pieces of software. So first of them is CosmoVis, mainly developed by David Abramov, who's going to talk about it next. And CosmoVis uses YT for several purposes, which he'll mention in his part. And then after that, I'll talk about Polyform, which is our Cosmic Web reconstruction software. I'm the main responsible developer of this, and we are not using YT right now, but we're actually considering or hoping to implement Polyform in YT, or rather the core component of Polyform in YT. So I'll tell you about that in the end. Let's jump to David's talk, and he'll tell you more about CosmoVis.
All right, thanks, Oskar. Yeah, I'm David Abramov. I'm a PhD student in the Creative Coding Lab with Angus Forbes at UC Santa Cruz. And I just wanted to mention again, Joe Burchett has been like very instrumental in like getting this project off the ground and like really having the vision for like what it should be doing and how it'll really like help astronomers. Oh, Oskar, can you go to the next slide? Yeah, go banana slugs. All right, so just a brief overview. What is CosmoVis and what does it do? So this is an interactive data visualization tool where we're loading in and rendering these big box cosmological simulations directly in the web browser. We're able to display gas, dark matter, and star particles within a unified framework. So we're displaying gas and dark matter as like a volume, and then star particles are like embedded as stars within that volume. And then on top of that, we're able to probe the simulated universe with what we call skewers, which then are used to generate synthetic spectra using a combination of YT and Trident. And then highlighted here are like the two steps that we really use YT for. So when we're loading in and like pre-processing the data, YT has some really great functionality in order to get it into a form that we can adjust in the web browser. And then for probing the simulated universe, Trident is like super instrumental to create these synthetic spectra that like map to the actual like instrumentation on the Hubble Space Telescope. So we can try to bridge the gap between these simulated universes and the real universe, which Oskar briefly mentioned, like there's a little bit of a challenge there, like comparing the two. So with that, let me share my screen here. Yeah, so what I have here is CosmoVis. I've pulled up a 25 megaparsec Eagle simulation. So right off the bat, let me move this over here. Like we're able to select in a few different simulations, select a grid resolution. This maps to like the number of voxels across that we've like voxelized the simulation into a volume. And I've already dropped a skewer here, so I can use these little scrubbing tools to like scrub in and select a galaxy and really hone in. Because like when you have like the whole simulation open, like it's just kind of really overwhelming. Like there's so many different galaxies that you can zoom in and look at. But over here, I found an interesting looking galaxy. It seems like there's this bubble of like ejected mass outside of like this super cluster of galaxies. And I've drawn this skewer here. So down here, there's this observe panel. I can drop a few more, for example, but basically in like the direction of the camera. Oh, it looks like it doesn't want to drop any. Oh, there we go. You can drop these skewers, and if I rotate the view, you can see the skewers have appeared, and then you can kind of like filter them down to just like a little area that you're focused on. And then if you hit request spectrum, it lets you know that it's generating a spectrum. And over here in my console window, underneath the hood, we have Trident computing those spectra. And while that's generating, here's this preloaded one that I have here that's cutting through this galaxy. And we offer some functionality for you can like really hone in on a particular like wavelength. Here, the other skewer just appeared. So say you wanted to inspect hydrogen 1 and wanted to look at it in terms of wavelength, you can easily compare across different skewers some kind of profile that would match what you would expect from like a actual observation. Under this layers panel, we provide more functionality for just like visualizing the data. So you can, so right now I have temperature. Oops, not that one. No, did not mean to click that. So that means nothing. So let's go back to temperature here. So with this dropdown, you can select different attributes. So these are just different fields that we've pre-processed from the data using YT. So you can look at density or entropy or iron or mass or silicon or temperature. So when you open it up, we're defaulting to temperature right now, and you can change the ranges. So by default, we kind of like shrunk it down to like a smaller temperature range, but you have some control over like what like the min and max value you want to look at for the data. So maybe you're only interested in a particular temperature regime. You can really check out like the gradient within that. Yeah, and then we're also visualizing dark matter, which appears in purple here. So you can turn on and off different layers. So you can just see like one particular particle type that you're interested in. And then we also provide the option to adjust these star sizes. Just in case, like depending on the resolution of your screen, maybe you want some more fidelity in that aspect. I can open this back up. Yeah, and this has been in development for about a year now. And yeah, I think we've made some really great progress over the past year. And Oscar's been very helpful with like fine tuning the volume rendering. So stop share, and then we can go back to the slides. Yeah, so just to briefly go over the architecture of CosmoVis. So up here on the top, we have like the CosmoVis interface that you just saw. So for the visualization, we're using the library 3.js to make this 3D interactive interface. And then D3.js we're using to load in the data. And then so that web interface also has that interactive analysis component where you can drop the skewers, request a spectrum, and then they'll get generated on the server side. And then on the bottom, we have this AWS cloud computing backend. So what you just saw is actually running locally, but it's designed where it can be deployed onto a server and like hosted as a static website. So within the AWS architecture, they have like an S3 like storage solution, and then on the right we have like our EC2 compute instance, and then this is all contained with like a Flask web framework. So we have like a Python like function that's like always running, and it has YT and Trident and multi-processing implemented. So, and then Flask is like Flask.io is being used to like talk between this front end interface that you get to interact with, and then the back end, which is offloading that computation for the spectrum, which is nice. And then we're able to output synthetic data products from there. So the spectrum that you generate that gets sent to your web browser, you can then download in a FITS data format that you can like easily plug in with your other astronomy analysis tools. So how we use CosmoVis or YT and CosmoVis. So there's two main components. So on the left here, we have like load, voxelize, and export cosmological simulations. So that screenshot on the left was taken back in like, I want to say like February or March. And this was before we started implementing a volume rendering. We were literally taking like each individual particle that existed within that simulation, and I exported them. And then we were visualizing those particles separately within like a 3D space. And this worked fine for like the smaller simulation. So I'll talk about like the 12 megaparsec box, which is like the smallest one we worked with, which is maybe like a gig in total size. And then, but we're also looking at 100 megaparsec boxes, which the largest one that Oskar showed, the TNG 100 that we worked with, was 2 terabytes in size. And so just like the number of particles is just astronomically greater than like the small box. So the particles worked fine and it looked pretty good for the small box, but like scaling up, it definitely was problematic. But what YT has, there's a super helpful function. I think it's called like create arbitrary grid, but basically you can give in like the start and end coordinates for like the box that you want within the simulation, as well as like the number of voxels across on each side that you want. So for any gas attributes that we were interested in, and the dark matter density, we were able to voxelize those fields. Those are a much better, like more compressed representation that we can then use in the volume rendering integral and display in the web browser in real time. And then on the right, we're using a combination of YT and Trident to generate the synthetic absorbance spectra. So as I mentioned before, we're using Flask and Socket.io to like send these messages back and forth between the front end and the server where the computation is happening. Basically, the front end sends, when you request the spectrum, it knows like what simulation you have open. It knows the start and end coordinates of those skewers within the coordinate space of the simulation. So it's able to then take that information, munch it down, and spit out the spectrum. And it just sends back like a little message with all the data points in there. And then D3 is being used to display those graphs interactively in the browser. Some of the challenges we've come across using YT is really only when working with the very large data sets. So these 100 megaparsec boxes. I'm not entirely sure if it's like a Windows thing or what, but basically what has happened to me is I've encountered overflow errors when loading data into YT. And so far it's only been with these like super large boxes, and it doesn't seem to affect all particle types the same. So it's weird, like I'll be able to extract the gas and the star particles, but then for dark matter, because of the overflow error when like creating the indexing when it's like loading in the data, it'll say something like can't access like index of a negative number, which like corresponds to like, I guess, the number of particles. But I found a workaround. At first I was like, well, this, I can't get past this. But then I like started poking around in the source code, and maybe offline I can like bring up where this is. But basically somewhere there's like an np.sum where it takes in an integer, but then the sum breaks down once your integers become too large. So I converted it first to a float, then back to an int after like it actually computes the sum. And then it started working just fine. But my computer doesn't have enough RAM to then continue on down the line with the actual processing for some of it. And then another thing is just, once again, with these very large boxes, and I don't think it's anybody's fault necessarily, but it just seems to be a little bit slow spectrum generation. And this is more of like a Trident issue, but I know Trident relies on YT, and I'm not entirely sure like how those like interface all the way. But not, yeah, both tools, not to discredit either tool, both tools have been invaluable in making this project. Yeah, you can go to the next slide. Yeah, and with that, keep an eye out for early next year. We're hoping to do like a public release of CosmoVis, kind of like 2 versions. One will be hosted online with some selected data sets that we've pre-processed and we'll make available for just like accessibility, like in the community. Like these data sets are so hard to access, like you need a powerful computer to like download them and like process them. So that's one aspect, is like making this publicly available where citizen scientists can probe the universe and gain some kind of understanding themselves. And then also we want to have like a packaged application where people will be able to load in their own simulations or whatever simulation they're interested in.
Cool, and you all have about 5 more minutes before the question session.
Oh, okay.
Okay,
Thank you.
That's perfect. So let me very quickly tell you about Polyform, which is a tool that we developed to reconstruct the cosmic web from observed galaxies. So this is a little snapshot of 37,000 galaxies from the Sloan Digital Sky Survey, very low redshifts, so very close to us, relatively speaking. And yeah, the task in this whole effort has been to actually discover the cosmic web just from these galaxies. So reconstruct the complete three-dimensional map, which also gives you densities and all the structures of the cosmic web from this data. So the inspiration for this work was actually art. So this is some really cool simulation art based on the Physarum polycephalum organism. This has been made by Sage Jensen and pretty much inspired the whole project down the line. Physarum polycephalum is a very ancient organism called protist. It searches its environment for food by just following chemical gradients. And by doing so, it kind of builds these networks interconnecting the food sources. So we thought this is a very nice metaphor for actually the cosmic web. It turns out that Physarum is very good at building transport networks. So for instance, this is a reconstruction of the Tokyo railway system using the actual organism, physical one. But we cannot rely on the physical one. It's just too messy to handle and can't handle big inputs. So instead we use a simulation. What the algorithm, we call it MCPM, standing for Monte Carlo Physarum machine. So what our simulation does is it has a swarm of agents that explore the environment, and they do essentially 3 things. They sense their environment, they sample in which direction they should move based on that sensing, and then they just update their position, so they move forward by 1 step. And chaining these 3 steps, they essentially perform a random walk through the domain, and they're trying to follow a signal emitted by the galaxies. So pretty much the same way as SlimeMole searches for food, the agents of our simulation search for the signal of galaxies and therefore interconnect them. What does this look like in action? Might be here. So the red dots are the galaxies and the white dots are the agents of the model. And you see when unleashed into the data, they actually kind of explore along the filaments and start creating a map of the environment. And when you let this run for about a minute, you actually get a converged map of the cosmic web from just galaxy positions. So yeah, this map very well aligns with the galaxy data. So here you have these yellow blobs are the galactic halos, and this purple trace is actually the filaments reconstructed by the simulated slime mold. And what you can clearly see is that this map actually very nicely aligns with all this data. So based on this, we actually created the first continuous and consistent map of the cosmic web, at least from the Sloan Digital Sky Survey data. We've done a bunch of really cool science based on this. I don't really have time to talk about it. So I would encourage you to just check out the website of the project and just check these beautiful papers. Polyform itself is mainly a volume renderer, so it uses an optimized hardware volume rendering to actually show you different modalities to slice through the data and do all these things to actually inspect the reconstruction both for the sake of doing the reconstruction and then analyzing what comes out of it. So, for instance, we in the study that I mentioned, a couple of minutes ago, we studied the Illustris TNG100 simulation, which is the same data set that David was showing you visualized in CosmoVis. But here we focus more on kind of the meta properties of it. So what is the kind of density breakdown of the cosmic web, gas density? What is the orientation of the filaments, as I mentioned before? How do the galaxy colors relate to the overall large-scale structure, etc., etc. So several different tasks. We also have a high-quality volume rendering, so with global illumination, that actually shows this data in a completely new light, no pun intended. So here you have the galaxy is rendered as these red kind of dots illuminating the whole volume, and then the cosmic web is the yellow to blue gradient on top of it. Anyway, most important is Polyform doesn't use YT currently, but we definitely want to consider implementing it within YT. So in the future, we want to expand the search to higher redshifts, to more complex data sets. And what implementing MCPM as the core algorithm would do within YT would just allow people to get fast and versatile way to reconstruct the cosmic web based on, for instance, just the galaxy data, but also simulated halos. So it's fit both for simulations and observations. And yeah, we'll start looking into this as we continue developing MCPM. The key step of making that happen is making the algorithm more autonomous, so it will function kind of as an AI, and then you really don't have to have this high performance visualization component, but rather just call a function in Python and get the reconstruction in a minute or two. So these are our plans, and we would really welcome any feedback that you might have for this endeavor. So with that, I thank you for listening, and this is our contacts. Here are some links, so feel free to take a picture of this slide, and yeah, go banana slugs. Thank you.
Cool, thanks. I'll clap for everybody. Wow, this is very beautiful. Thank you. Thank you both for waking up early to show us this amazing tool. Great. Do we have some questions? Let's see, give a moment for people to raise hands, check and see. I don't see any. Oh. Just stop my video. My connection's unstable again. Okay, Maxime.
Yeah, thanks. Thanks a lot for the talk. I had seen the paper a couple months ago. I don't know, time has lost meaning now. But I'm just wondering, like reconstructing the cosmic web for like 40,000 galaxies, how expensive is it? Because that's the kind of number of halos you get in cosmological simulations. So like, is it something that you can do like in post-processing easily and like tweak the parameters and visualize whatever you want? Or do you need like some more computational capabilities?
It's surprisingly efficient. So we can use up to like million halos in the simulation, and the simulation doesn't really run much slower when you have a lot of halos. But yeah, basically tens of thousands to millions of points you can reconstruct interactively. So you just load it up and the simulation runs. Like the videos I showed you are the real-time capture from the software. It usually takes like a minute or two for the simulation to actually converge to to the cosmic web, to a stable solution. Of course, when you load up new data, you don't really know what's the right parameters of the model. So we calibrate that using simulations, and so you get like a good first guess for the parameters, and then you can interactively tweak them, and the software basically reacts interactively. And I would say if you would sit down to the software, not knowing anything about it, load the data, and then start fiddling with it, and fitting within like half an hour, you would get a decent reconstruction of the cosmic web.
That's really cool. And can you, like, I guess once you reconstruct the things, can you get the properties of, density along the filament or something like that?
You get a complete density field for the entire simulation volume. You can export that with a press of a button and then load it up in Python and do any further analysis. Joe, who's in here, has done that, and so he can tell you more about it.
Thanks.
Yeah, thanks for the question, Maxime.
Cool. There's also some discussion going on in the chat about kind of smoothing SPH particles onto a grid, and how big of grids are currently being handled by CosmoVis. But I'll let people kind of scroll through that. So, and we have another hand from Chris.
Hey, great talk. I'm curious if the structures that you reconstruct in the simulation, does it depend at all on where you release your particles that do the tracing? Like, do you see any difference either in structure or in performance?
Not at all. No, the initialization only matters in like how fast it converges. So this is the amazing stuff which we found about this. It doesn't get stuck in local maxima. It just has one globally optimal solution and gets there. Yeah, in fact, we usually start with like uniformly distributed particles, but for the effect of like, hey, slime was growing from the middle of the whole domain, I show it this way. So yeah, good question.
That's so cool. But both of these are totally amazing. Great. So if there's more questions, we should move them to Slack discussion. Thanks again, Oskar and David. That was great. And we have our